On page 190, we're going to be working with concavity and the second derivative test. All right, so first we've got to talk about what concavity is. It's a kind of complicated definition, but it's easy to see when you look at the graph. Okay? The definition is, let f be differentiable on an open interval. The graph of f is concave upward on the interval if the derivative is increasing on the interval, and concave downward on the interval if the derivative is decreasing on the interval. So the graph of f is concave upward if and only if f prime is increasing. The graph of f is concave downward if and only if f prime is decreasing. All right, so just that with no pictures, I don't know how in the world you would understand it or remember it. So let's look at the picture. Okay? Here we have two graphs. The one on the left is concave upward. The one on the right is concave downward. By looking at those, do you kind of get a sense of what concave upward means? Doesn't mean the function is increasing. It means that. That's concave upward. That's concave downward. Okay? The only time it's a little tricky is if it's not, if it's not as obvious. Concave up, concave down. Somewhere right around in here it switched, didn't it? Okay? We'll call that a point of inflection where the concavity changes. Now, so if it's actually kind of simple visually, why do we have this complicated definition? Well, because it helps us to find concavity and changes in concavity when we don't have the graph. So you got to realize you guys are actually learning calculus at a distinct advantage to everybody that learned calculus 20 years ago or more. Because you've got graphing calculators and you've got books with graphs all through the book. And y'all have done graphs for years. That graphs used to be a very difficult thing because you didn't have a graphing calculator and you didn't have the ability to reproduce them all that well for others to see. So you guys are a lot more visual. I want to say visual learners. That may not necessarily be right, but you learn things visually a lot more than people my age did because it's available to you. Okay? But look what happens. The definition actually does make sense if you look at the picture. It says f is concave upward if and only if the derivative is increasing. Now look at these little blue tangent lines they've drawn in. The slope of that one is negative. It's not real negative, right? It's not negative 1,000 or something, but it's negative. And then the slope of this tangent line's positive. Here the tangent line has a slope that's positive and it's steeper, so it's bigger. So right, as we moved around, the slopes of the tangent lines got bigger. They increased, didn't they? When the function is concave up, or actually I should say when the graph is concave up, the first derivative is increasing. Not necessarily positive, but it's increasing as you move from left to right. And then when the function or the graph is concave downward, look here, slight positive slope, negative slope, steeper negative slope. So the derivative is decreasing, isn't it? The slope, as we move from left to right, the slope of each tangent line is smaller than the one that came before it. So the derivative is decreasing. Notice also, when the graph is concave upward, the tangent lines are below the graph. When the graph is concave downward, where are the tangent lines? Above it. Okay? All right. Now, you're going to have to remember this. And you're not going to remember it right off the bat. All right, so if I tell you that the graph of a function is concave upward, what do you tell me about the derivative? It's increasing. If I tell you that the derivative is decreasing, what do you tell me about the graph? It's concave downward. Okay? All right, so it'll take a little while for that to sink in and for you to always remember that that's the way it works. But you need to take the trouble to remember that that's the way it works. Okay? Now, if we look here, if that just said F instead of F prime, where would F change from increasing to decreasing? At a critical number. And how do you find critical numbers? Yeah, where the derivative equals 0 or does not exist. So, since this says F prime instead of F, where will F prime change from increasing to decreasing? Now, we don't have a name for it yet, but where its derivative equals 0 or does not exist. And what do you call the derivative of the derivative? Second derivative. So see, F prime can change from increasing to decreasing or vice versa, where the second derivative equals 0 or the second derivative does not exist. So concavity can change, because right, if F prime changes from increasing to decreasing or vice versa, F changes concavity, doesn't it? So now let's take it then here. Here's what you need to be thinking. So where can the concavity of F change? Where the second derivative equals 0 or the second derivative does not exist. Okay? Now, if this just said F, if that said F instead of F prime, if F is increasing, what does that tell us about its derivative? Positive. So if F prime is increasing, what does that tell us about the second derivative? It's positive. So when a graph is concave upward, what's the sign of the second derivative? It's positive. All right, let's look at this the second one. If F is decreasing, its derivative is negative. So if F prime is decreasing, the second derivative is negative. So when a function is concave down, what's the sign of the second derivative? Negative. Okay? So we got to be careful with all that. I know it's not going to sink in real fast, but you're going to have to remember that. Because if you don't remember it, guess what? You got to refigure it out every time. Well, that's going to get old really fast to have to refigure it out every time. Okay? So, you with me? All right. If we have, let's look at both these at the same time. Here's the graph of F, and here's the graph of its derivative. So look, I'll trace it out here in red. Here we've got a function that's concave down, which means its derivative is decreasing. All right? We're still concave down. The derivative is still decreasing. Right about here, the graph changes to concave up. So now the derivative is increasing. We're still concave up. The derivative is still increasing. Yes? Okay. All right. Now let's look at this. Where does the derivative change from decreasing to increasing? At 0, -1. Okay? Where does the concavity of F change? Well, at 0. It's a different y coordinate, but at the same x coordinate, correct? So the concavity changes when, well, I'm not explaining that right. When the derivative changes from decreasing to increasing, that's when the concavity changes. Or when the concavity changes, that's when the derivative changes direction. Okay? Now, if this were just a function, where does this function change from decreasing to increasing? X coordinate, 0. So where would its derivative change signs? 0. If the function is decreasing, what's the value or what's the sign of its derivative? Negative. And if the function is increasing, what's the sign of its derivative? Could we graph the second derivative? Negative, positive. So, not only now can we take a graph of a function and sketch a rough graph of the derivative, we can now go a step further and sketch a rough draft of the second derivative. Rough graph of the second derivative, which could be a rough draft. Now, I could make you redo it over, 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 and over, and then do it again. Anybody's head hurt? Does it make sense? Does it scare you that you're going to have to remember all that? It'd scare me. I don't scare easy. Well, I like to pretend I don't scare easy. All right, so all this leads us to the test for concavity. And when we work an example here in a minute, I'll put all this in a table for you and make it easy, I hope, to figure out. But it works this way. If the second derivative is greater than 0, so if the second derivative is positive in an interval, then the graph is concave up. Why? Because if the second derivative is positive, the first derivative is increasing. And if the first derivative is increasing, by definition, the graph is concave upward. If the second derivative is less than 0 in an interval, then the graph is concave downward. Why? Because if the second derivative is negative, that means the derivative is decreasing. And by definition, if the derivative is decreasing, that means the graph is concave downward. Okay? It's one of these nice situations where no matter which end you start at, it's always true. A statement and its converse are true. If it's concave up, the second derivative is positive. If the second derivative is positive, then it's concave up. So you don't have to really worry about starting on one way and going the other. It works either way. Now, the way I've written it out, which I hope makes sense, let's see if it does. F can change concavity only where F prime changes from increasing to decreasing, or vice versa, or where F prime changes from decreasing to increasing. So, if F changes from increasing to decreasing, that's where F double prime changes from positive to negative, right? Increasing means derivative positive, decreasing means derivative negative. So if it's F prime that's changing, it's F double prime that's changing signs. Or where F prime changes from decreasing to increasing. So if F prime is decreasing, that's F double prime negative. If F prime is increasing, that's F double prime positive. Now, for this to happen, so we're working on intervals again. So the concavity can't change unless the derivative changes from increasing to decreasing or vice versa. The derivative can't change from increasing to decreasing or vice versa unless the second derivative equals 0 or does not exist. So, where are the only places concavity might change? Where the second derivative equals 0 or does not exist. We don't have a nice little name like critical numbers for where the first derivative equals 0 does not exist. We just call them possible points of inflection. Okay? So possible points of inflection occur when the second derivative equals 0 or the second derivative does not exist. Now, you can get away with just memorizing that for a lot of the problems. But then the ones that I think are easy and you don't, or you see a picture of something and you have to tell where something, you might be given F and you have to tell where the derivative is positive or negative, or given F prime and tell where the F is increasing, decreasing. I like those. You guys mostly don't. if you don't actually understand what's going on, you won't be able to answer those questions. You'll be able to do the book questions of, they'll give you a function and say, where does the concavity change? You can do that because you find the first derivative, find the second derivative. I'll show you how to do that. You'll get really good at it. But you got to understand the relationship between increasing, decreasing, derivative being positive or negative, and concavity. You got to understand the relationship between the graph, the first derivative, and the second derivative to be able to answer the less mathy looking questions. Fewer numbers. But those questions get to whether or not you actually understand what's going on. Okay? And they're tricky. You got to be careful. All right. So a point of inflection is where the concavity changes. Now, the fancy definition is kind of complicated. Let f be a function that is continuous on an open interval, and let c be a point in the interval. The graph of f has a tangent line at this point, cf of c. If the graph of f has a tangent line at this point, cf of c, then this point is a point of inflection of the graph of f if the concavity changes from upward to downward or downward to upward. The point of inflection is where the concavity changes. Okay? Now, it's possible, so you look here, right here is the point of inflection because the graph is concave up to the left, concave down to the right. Here's a point of inflection because it's concave down to the left, concave up to the right. There's another point of inflection because the concavity changes. It says notice that the graph crosses its tangent line at a point of inflection. Okay? So that's another clue to where they are visually. Because remember what we said? That if the graph is concave upward, f lies above its tangent line, downward lies below. So where the concavity changes, the tangent line is not above or below. Make sense? All right. Then like we've already said, the point of inflection can occur only where the second derivative equals 0 or the second derivative does not exist. Now, concavity can change without there being a point, like so. If we've got an asymptote, if we've got a graph that does that, and then that, the concavity changed at x equals c, didn't it? Because it's concave up over here, it's concave down over here. But did the concavity change at a point? No, because there is not a y-coordinate that matches up with the x-coordinate of c. So that leads to some awkward wording. We try to avoid saying that c is a point of inflection, and we try to remember to say instead the concavity changes at x equals c. At least for a while, if you call that a point of inflection, okay, but it's not really a point, is it? But since the function doesn't exist at x equals c, the derivative doesn't exist at x equals c, which means the second derivative does not exist at x equals c. So that's how it still fits the definition. Now, does that mean the concavity changes at every asymptote? Of course not. Because what if the graph is that? Well, it's still up. So just like not every critical number leads you to a max or a min, not every time the second derivative equals 0 or does not exist does the concavity change. Okay? All right. So that's concavity. We'll have to address this again, I think. Okay? Now let's talk about the second derivative test. In addition to testing for concavity, the second derivative can be used to perform a simple test for relative maxima and minima. The test is based on the fact that if the graph of a function f is concave upward on an open interval containing c, and f prime of c equals 0, then f of c must be a relative minimum of f. What? Let's think about that. Okay, how much of this is attached? I'm going to move this down for a minute. It says the test is based on the fact that if the graph of f is concave upward on an interval. Okay, so let's make a little interval. Let's make the graph concave upward. Okay? Now, and f prime of c equals 0. Where's the only place on that interval where the derivative equals 0? Right there. And since the graph is concave upward and the tangent lines are below the graph, isn't that a relative minimum right there? That's kind of cool. All right, we didn't have to do the where does it increase, where does it decrease. Okay. So similarly, if the graph of a function f is concave downward on an open interval containing c, and f prime of c equals 0, so where's the only c where the derivative would equal 0? Right there. F of c must be a relative maximum. It is, isn't it? So that's cool, I think. And it really is sort of simple. Less work, I'll put it that way. Less work than the first derivative test. I don't know if it's simpler. Does that make sense? All right, good. Now, here's the thing. Notice in both cases, it's f prime of c equals 0. Does the second derivative test here address the possibility of finding a max or a min when f prime of c does not exist? Second derivative test does not work for critical numbers that you find where the derivative does not exist. It just simply does not work. Okay? All right. Now, let me try to move this down just a bit. Now, let's follow the logic here. Okay? I want you to understand. I know you'll forget it, and we'll have to explain it again. But let's understand it the first time, and then I'll explain it again Monday, and it'll come back to you, and I'll explain it again Tuesday, and it'll come back to you. Okay? But concentrate with me here right now. Okay? It says let f be a function such that f prime of c equals 0. So we got a critical number where the derivative equals 0. And the second derivative of f exists on an open interval containing c. If the second derivative is greater than 0, in other words, the second derivative is positive. Think back to our concavity discussion. If the second derivative is positive, the first derivative is increasing, which means the function is concave up. So second derivative positive means concave up. So we've got a function that's concave up, and the derivative equals 0. That's a relative minimum. Part 2. The second derivative is less than 0. So the second derivative is negative. Okay? Second derivative negative means first derivative is decreasing. First derivative decreasing means the function is concave down. Then where the derivative equals 0 is a relative maximum. Okay? Now, get this. Derivative positive, second derivative positive, relative minimum. Positive matches up with minimum. Second derivative negative, relative maximum. Negative matches up with maximum. People get that messed up on the quiz sometimes. Okay, you think you got every possible thing memorized, and then you blow it on something like that because, you know, positive and minimum is not really the first thing you connect, is it? Okay, but that's the way it works. All right. Now, why does all this work? Because we know where things change. Okay. The second derivative can only change from positive to negative by going through the second derivative equaling 0 or not existing, which is where the concavity can change. Okay? So we know that if the second derivative is positive on an interval, that it's all, well, if we know the second derivative does not change sign, then we know the concavity does not change. So we don't have to worry about, well, are we leaving anything out? Are we missing anything? No, we're not. Okay, as long as you make your intervals in between where the second derivative changes signs, then you're okay. All right? Now, I'll show you the test here in a minute. You're going to like the second derivative test. The test itself is simple. Now, it says if f double prime of c equals 0, the test fails. The second derivative test only works if the second derivative is positive or negative. It doesn't work if it's 0 or does not exist. Okay? That is, f may have a relative maximum at c, a relative minimum at c, or neither. So, then you have to fall back to the first derivative test, which y'all did a pretty good job of. Okay? All right, here's the way I've worded the second derivative test. Maybe this makes more sense. I mean, I intended for it to. Doesn't mean it does. But second derivative test. This works when f prime of c equals 0, not when f prime of c does not exist. So if you get critical numbers from the does not exist category, don't even bother with the second derivative test. Okay, it's not going to work for those critical numbers. Now, f prime of c, if f prime of c equals 0 and f double prime of c is positive, if and only if f is concave upward and f of c is a relative minimum. So, the if and only if, it goes either way. If I know the derivative equals 0 and I know the second derivative is positive, that means f is concave upward, which means at c, there's a relative minimum. I can turn all that around. If there's a relative minimum at c and the graph is concave upward, that means the second derivative is positive and that the first derivative equals 0 there. Okay? F prime of c equals 0 and f double prime of c is negative. If and only if. All right. Second derivative being negative means f is concave downward. And if you've got concave down and a horizontal tangent line, that's a relative maximum. Then you can follow it backwards if you want to. And if the second derivative equals 0, no conclusion. Go back to the first derivative test. So if we look here, we have a function that's concave upward. I want to do something different with this. F is concave up. What's that mean about f prime? Increasing or decreasing? Increasing. And what's that mean about f double prime? Positive or negative? If you know any one of these three things, you can conclude the other two. And when all that happens, look back to the graph. What happens where the derivative equals 0? Relative minimum. Okay? Then let's look over here. On this one, f is concave downward. What's that tell us about f prime? Increasing or decreasing? Decreasing. And if f prime is decreasing, what's that tell us about the sign of f double prime? Again, if you know one of those three things, you conclude the other two. When all that happens, and the derivative equals 0, we have ourselves a relative maximum. So, going back to the second derivative test. So that's talking concavity. Now look at the second derivative test. When the derivative equals 0, and the second derivative is positive, we got a minimum. When the derivative equals 0, and the second derivative is negative, we got a maximum. All right. Now, I've attempted to say basically the same thing several different ways. Have you realized I'm saying the same thing? It's good. Lots of times classes go, oh, I didn't know you were saying the same thing. Because it's hard. I know this is hard. All right? This is why I'm trying to be so careful. I've confused people terribly in this section over the years. I'm trying to avoid that. Because, a lot of you are Cardinals fans. If you're Cubs fans, I'll teach it to you wrong. Let's do a couple from your assignment. I'm on page 195. We're supposed to, for number 6, we're supposed to determine the open intervals on which the graph is concave upward or concave downward. And they tell us the definition of the function, y equals negative 3, x to the blah, blah, blah. When I'm given a graph, do I need to know what y equals? No. So, first thing I do is ignore that, and I look at the graph. All right, I've got concave up, starting at negative infinity. And let's see, concave up, concave up. Now, it changes from decreasing to increasing, but it stays concave up, doesn't it? So it looks like negative 2. I mean, look, if it's negative 2.001, we're still calling it negative 2, right? It looks like negative 2 to me. So negative 2, concave up. Then, starting at negative 2, our graph is concave down to about 0. So look, it's increasing, but the concavity is downward, isn't it? Okay? Concave up doesn't mean increasing. Concave down doesn't mean decreasing. Okay? But why do I know it's concave down there in the blue part? Because if I drew a tangent line, wouldn't the graph be below the tangent line? That's concave down. Okay? So, from negative 2 to 0, concave down. Technically, we're supposed to say upward and downward, but put up or down. Don't give me arrows. People do that sometimes. It drives me crazy. I don't want an arrow. I want the word up or the word down. Okay? And we're back to concave upward. I think I passed it, didn't I? What do you think? Where does it switch? 2-ish? I would say 2-ish. And it's hard to be precise, but 2-ish. So from 0 to 2, concave up. Is it concave down the rest of the way? Yeah, it's increasing for a while, but the concavity is down, and then it stays that way. So from 2 to infinity. Does all that make sense? Questions? All right. Number 12. Find the points of inflection and discuss the concavity of the graph of the function. All right, so this looks more like a math problem here. Points of inflection. Where can the concavity change? When f double prime equals 0 or does not exist. Okay? So when they ask you to find points of inflection, they're asking you, where does the concavity change? Because concavity changes at a point of inflection. Okay? So that means we've got to find the first derivative, then the second derivative, and then find where the second derivative equals 0 or does not exist. Step 1. Well, I mean, this is calculus. So if you didn't know what else to do, you would take the derivative. F prime of x then equals 6x squared minus 6x minus 12. they don't ask us about extrema, we don't have to find critical numbers. Okay? Take the second derivative, 12x minus 6. Now, like we always factored the first derivative because it made it easier to find critical numbers, factor the second derivative, it makes it easier to find possible points of inflection. So I'll factor a 6 out. We always used to write the sentence that said critical numbers occur when f prime of x equals 0 or f prime of x does not exist. Now we say a point of inflection can occur only when f double prime of x equals 0 or f double prime of x does not exist. All right, the second derivative is a polynomial function. It exists, doesn't it? But it can equal 0. At least I think it can. We'll solve it and find out, won't we? So I set 6 times the quantity 2x minus 1 equal to 0, and I just state that f double prime of x exists. And then I solve. Divide both sides by 6, that's gone. Add 1 to both sides, you get 2x equals 1. So x equals 1/2 is a possible point of inflection. Notice I didn't say that it is a point of inflection. If there is a point of inflection, it happens when x equals 1/2. There may not be a point of inflection. There's no rule that says the concavity has to change. Okay? But if it does, that's the only place it can happen. With me? Now, I'm going to show you the table I use for the test for concavity. The book does it a different way, kind of like the first derivative test. I think this is genius. I didn't come up with it myself. Somebody else taught it to me, and it's the best way I've ever seen. So, if you go out on your own, okay, but you got to be able to explain everything that I'm going to put in this table. All right? So the test for concavity looks a lot like the first derivative test. I have an interval, but these intervals are not based upon critical numbers. They're based upon possible points of inflection. I have a test number, again, based upon the possible points of inflection. I don't care about the sign of the first derivative anymore. It's the sign of the second derivative that's going to tell me what my conclusion is. Bless you. All right, so we only have one possible point of inflection. So we're only going to have two intervals because there's only one break, okay? So we start our first interval at negative infinity, and we go to 1/2. Then our second interval starts at 1/2, goes to infinity. Pick a test number in each interval. Whenever I can use 0, I like to use 0. So I'm using 0 and 10. Now, when x equals 0, what's the sign of f double prime? So you go to the second derivative, replace x with 0. 2 times 0 is 0. I'm right here. 2 times 0 is 0. 0 minus 1 is negative. 6 times negative is negative. So the sign of the second derivative is negative. And then when the second derivative is negative, our function is concave downward. And I'll refresh your memory again. Why? Because if the second derivative is negative, the first derivative is decreasing, and the first derivative decreasing by definition means concave downward. All right, now let's find the sign of the second derivative when x equals 10. Well, back up here to the second derivative. 2 times 10 is 20. 20 minus 1 is positive. 6 times positive is positive. When the second derivative is positive, concave upward. So is there a point of inflection when x equals 1/2? Yes, because the concavity changes. That's where the point of inflection is, where the concavity changes. Now, and some of you were a little bit loose with your notation on the quiz. All right, x equals 1/2 is not a point. To get a point of inflection, we need a y-coordinate that goes with it, don't we? Should I use the second derivative, the first derivative, or the function to find the y-coordinate? Function. So you go back all the way up to the top, put a 1/2 in for x, and it turns out that y is negative 13/2. So the point 1/2 negative 13/2 is a point of inflection. What you can also write, especially if you get just one of those horrible functions that it's difficult to evaluate, if not, well, it won't be truly impossible, but next to impossible, instead of writing the actual point, you can say something like, there is a point of inflection at x equals 1/2. Don't say that x equals 1/2 is a point of inflection. Just say there's one there at x equals 1/2. A little nuance, but I like to be technically correct. And I need for you to be you need to be technically correct when you take it in college. Okay? No, not as far as we know. Because it's not at a, see, as far as we know, 1/2 is not a critical number. See, if I do that, that's concave down the whole time. So the concavity doesn't change, yet there's still an extreme value. Extreme values in concavity don't really have anything to do with each other as far as where they happen. What does matter is this. We have concave down, which means f prime is decreasing, which means f double prime is negative. But see, it's negative everywhere. Now, when the second derivative is negative and the derivative equals 0, that's when you have your max. Or if the second derivative is positive and the derivative is 0, that's when you have your min. See, we got the second derivative negative, second derivative positive, but we didn't find that at critical numbers. See what I'm saying? Does everybody see that? I'm glad you asked that. Because see, this, like in this instance, the second derivative is negative everywhere here. Well, there's not a max at every one of those points, is there? The max only happens when the second derivative is negative and the first derivative equals 0. So both those things have to happen at the same point to get a maximum. Make sense? It'll make more sense once I show you the second derivative test. Okay? Which, man, somebody talks too much. Let's try. And I'm going to have to give you homework over the weekend. I'm sorry, but I got to. Find all relative extrema. Use the second derivative test where applicable. All right, and I'm going to go fast, okay? I got to. So, number 31, f of x equals x cubed minus 3x squared plus 3. This is calculus, so the first thing we do is take the derivative. 3x squared minus 6x. We're looking for relative extrema this time. Relative extrema occur only at critical numbers. So we've got to find the critical numbers this time. So I take that first derivative and I factor it. Skip a couple of spaces. Literally, skip a couple of spaces. And let's find our critical numbers. Critical numbers occur when f prime of x equals 0, or f prime of x does not exist. F prime is a polynomial function. It exists. So you set the derivative equal to 0. 3x times the quantity x minus 2 equals 0. What are our two critical numbers? 0 and 2. X equals 0 and x equals 2 are critical numbers. Okay? Now, what was going on back up here where we skipped these two spaces? If we're going to use the second derivative test, we got to have the second derivative. So, the easiest way to take the second derivative is from here, isn't it? The unfactored version is easier. So the derivative would be 6x minus 6. You don't have to factor that, but I did. Makes it a little bit easier if you factor it. And I'll show you why. Unless the bell rings. Here's our second derivative test, and it's in a table, and it looks different. No interval. And not a made-up test number. C stands for critical number. So I'm going to use, in this case, 0 and 2. So this is what we just got through talking about. I know the derivative equals 0. That's a possibility for a max or a min. The sign of the second derivative will tell me which it is. Okay? So we want the sign of the second derivative. So we go to the second derivative right here, and we plug in 0. When x equals 0, is the second derivative positive or negative? It's negative. When the second derivative is negative, when the first derivative equals 0, that's a relative max. Second derivative negative means concave down. Derivative of 0 means horizontal tangent line. That's a max. At 2, if we plug a 2 in here, our second derivative is positive. When the critical number, or when the derivative equals 0 and the second derivative is positive, that's a relative min, because that means this is going on. Second derivative positive means concave up. Derivative equals 0 means horizontal tangent line. That's a relative minimum. See how it all ties in? And then write it correctly. Don't say x equals 0 is a relative max. A lot of you did the points. I liked that. So 0, 3 is the relative max, or f of 0 equals 3 is the relative max, or the relative max occurs when x equals 0. So be careful with the way you write it, what you're saying. And I'm going to give you a little bit less homework than I had intended, but it's still going to hurt. That's it.